All right, hello and welcome to Algorithms Live. And this week I've got this problem for you all. This is a Fibonacci Machine problem. It's from Algorithmic Engagements 2009, which is, I guess, part of the Polish IOI training. So I don't know too much about algorithmic engagements other than they have really good problems. And so the focus on this is really just to show a segment tree problem where you have to modify the segment tree. So a standard segment tree won't do. Really the purpose of this problem is just figuring out the modifications to segment tree that make the most sense and then implementing it. And so I think this will just demonstrate just how flexible segment trees are. So if you couldn't figure this one out, the problem is in the blog. So I definitely recommend giving this a try if you're watching this later. And give the problem a try yourself. Try to figure it out. And if you can't figure it out, then this video should help. All right, so we'll dive right in. I think the problem itself is really neat. So it's based off the Fibonacci numbers, first of all. So we can just, we'll just write down the precise, yes, OneNote updated and gave me this very fancy Galaxy pen that I've been using all week for lectures and things. So let's start off. I think it also updated pen sizes and things. So I'm going to play around with a slightly smaller pen size. So we have here is the Fibonacci numbers, recursively defined, just should be familiar to everyone. And so the main thing is they start at 0, f of 0 is 0, f of 1 is 1, and we can define the Fibonacci numbers this way. So I could make a definition for Fibonacci, so maybe 0, 1, 2, 3, something like this. Just make a table. And then the Fibonacci numbers, of course, are 0, 1, 1, 2, 3, 5, 8, 13, and 21 here. And it continues on. But this will help me describe the problem a little easier. So the idea with this problem is you're given an array, and initially everything in the array is zeros. So maybe 7 zeros like that. And then we select some range to update, and everything just increments by 1. So we end up getting a +1 here. And then let's say we do a few more updates. So our array at the very end of this could look something like this. Maybe something like that. And then I could ask for some sort of query, maybe select that as my query range. So I could say query, and the ranges all don't have to be the same size for the query. And what I report is I take the number in that array, and I take that Fibonacci number. Oh, so f6 plus f5 plus f8, something like that. And so that ends up being my Fibonacci numbers. So I just take these numbers here and sum them together. And these can get really large really fast. You want them under modulus. Don't know what I'm doing tonight. So I believe this is 5 and this is 21. So we just get a sum like this. And you can intersperse the queries and updates, pretty standard for interval tree type questions or segment tree type questions. And so we have n is the array size. K is the number of updates and queries. So you can intersperse them. You can have any number of updates, any number of queries. And the big thing in this problem, everything's up to 10 to the 5th. So our runtime needs to be pretty good. In this problem, we're looking for something like this k log n style runtime. So standard segment tree. If this was a min query, that's the runtime we'd be getting with our normal segment tree problem. So the big thing to look at here is the updates on this problem are very just similar to the standard segment tree problem. If we coded in episode 4, we did plus value there. We're just going to do +1. So if we select some range, it increases the value. So the updates are very similar. So if I just look at the updates, something like this, I'm just applying +1 at the node, and that's the change that I want to push down to my children whenever I do my lazy prop. So lazy prop still works here. Ooh. And I can, if you just look back at episode 4, you can see how all of that works. But the really tricky part is now I need to do these sum aggregates, and my aggregates aren't on these numbers here. The aggregates are on the Fibonacci numbers of those numbers. So that makes things a little more complicated. So you could, I've seen people try to work this problem. We actually worked it at this training camp this week. It's just a sample problem. So some people are trying to, some ideas that were thrown out were maybe try precompute all f of n. You could do something with that. If we have all the f of n under modulus, maybe we could pull things out, but then you end up having these weird problems gathering numbers out of, pulling those out of the modulus. Eventually, some people made these observations. F of n is at most, or n, for f of n is at most 10 to the 5th, because everything updates by at most 1. So everything just updates by +1. So if you're looking at this, trying to get that nth Fibonacci number, you're never going to need more than that 10 to the 5th Fibonacci number. So that's a convenient, useful thing to know. And so we need to start thinking about the queries a little bit differently, maybe. And so this kind of leads to a dead end up here. I'm sure you all probably came up with some ideas on how to get there. So here's how I like to think about it. If I'm doing a segment tree type problem, I know that in my left and right child, I have some information that I need to store. I need to store some kind of sum of Fibonacci numbers. And in the left subchild, I'm going to have that information. The right subchild, I'm also going to have that information. But what I really need to do here is I need to have this +8. There could be a delta in my left child, and maybe +6. So I could have different deltas in my left and right child. I need to be able to aggregate this somehow. So I need to be able to take the sum of Fibonacci numbers right here, be able to progress those Fibonacci, all those Fibonacci numbers up by 8 somehow, and then get some sum so I can save it in the subtree. Because the whole end game here is, if you remember in segment trees, we'll end up at a node that completely covers the interval we care about. So we need the answer in that node in some form. Now you can always store more information than you need, and you're going to see that in this problem. You're going to have some auxiliary information that's going to help us. So let's think about how this works. So what's really being stored is we have some sum of Fibonacci numbers. F8 maybe, F6 maybe, F5 maybe, something like that. And if we're applying a +6 delta change, then the sum after that delta change here to get to the left is going to be something like F14, F12, F11, something like that. So we need to be able to represent this change somehow. So how do we progress Fibonacci numbers? So one thing is, if you want to calculate really large Fibonacci numbers, there's this wonderful technique called matrix exponentiation. And the idea is to write a matrix that can encode the recurrence of what you want to try to figure out. And then if you can raise that matrix to a really high power, there's a technique for doing that. What you can do is you can just multiply your base cases times that recurrence matrix and spit out the recurrence. I'll show you how that works for Fibonacci. So let's say I have Fibonacci numbers here. Here are my base cases, f of 0, f of 1. Doesn't really matter what the base cases are, but I'll add those numbers. So in our case, it'd be 0 and 1, but for this case, we'll just show that. And what I'd like to do is I'd like to multiply this by some kind of matrix and get out the next iteration of Fibonacci numbers. So I'm basically just sliding the window over. So I'd like this to be is f of 1 and then f of 2. So what this is almost like you're doing the DP space saving style. And here's your DP table right here. And the next row of your DP table is just the 2 slid over. So if you applied it again, you'd get F2, F3, F4, or F3, F4, and so on. But we only have access to F0, F1, so I can just rewrite these in terms of the recurrences. And so what I'd like to do is I just basically reverse engineer this recurrence to be this matrix. So I need this to come out to F1. Well, if you look at how matrix multiplication works, I can go here. If you do matrix multiplication, this row times this column will give you this term right here. So we get f of 0 times 0 plus f of 1 times 1. We get f1. And then if I do the same thing in another piece, I'd make these both 1s. Then I can do f of 0 times 1, and f of 1 times 1. I get this term right here, which we all know is f2. So that's just how matrix multiplication works. All right, so we get this nice looking recurrence here. You can basically make a linear recurrence kind of matrix for any linear recurrence. You can just make this style matrix. So it's very handy for solving those kind of problems. Okay, so if we're dealing with this kind of recurrence, this kind of matrix, one thing we can do is take that matrix and now raise it to the kth power. Look what happens to some of these Fibonacci numbers. So if we have f of x and f of x plus 1, these are our two positions, then what we'll get out is it'll slide it by k by doing this multiplication several times. We get f of x plus k and f of x plus 1 plus k. So it's just sliding the matrix a lot further. So if we end up getting out to 100, let's say, just for example, and we were at f of 3 and f of 4, what we would get out is f of 103 and f of 104. So it's just a nice way. It doesn't even matter where we are in this matrix here. We can just slide it forward by having this kind of matrix. All right. So we don't want to deal with individual Fibonacci numbers. We're really trying to deal with sums. So I want to show you what happens if we have sums of Fibonacci numbers and we multiply it by this matrix, because that's much more interesting. So we have f of 3 plus f of 27. And then we have f of 4 plus f of 28. Watch what comes out of here. So these are kind of grouped together. So what'll happen is this will be multiplied by 1. You end up getting in the first row f of 4 plus f of 28. So that's not very surprising in terms of how this progresses. But what you get is this term plus this term in the base. And I'm just going to rearrange some of those numbers right here. So I get f3 plus f4 plus F27 plus F28. And that's what this looks like, which we can rewrite. So we have F4 plus F28. We can group this together now and get F5, and group this together now and get F29. So addition is associative and commutative, so we can do this manipulation. So if we are dealing with sums of Fibonacci numbers, everything is still okay. And then even if we bring this to a higher power, so I raise this to a k, I could have several Fibonacci numbers. We have F4, maybe F21. These are the sums of things in the matrix. Of course, in our problem, we're just going to have one number here, not these terms. But I can just show you, it doesn't really matter what these things are. The aggregate is still useful in terms of progressing the Fibonacci numbers. I multiply that by k. What I'll get here is I'll get F4 plus k plus F21 plus k plus F of 6 plus k. And then the base, right here, I get F of 5 plus k, F of 22 plus k, and F of 7 plus k. So the sums really work out here. And in terms of our vector, we could just generalize this now. It's the sum of the ith Fibonacci number that was there plus k, and the sum of the ith Fibonacci plus k plus 1. And so what came in was the sum, this piece right here was the sum of f of I, and then sum of f of I plus 1. So we can just progress entire sums of Fibonacci numbers very quickly. So we can do a lazy aggregate. If, let's say, just for notational purposes, this is our Fibonacci matrix. I'll just call that M. And if I want to get my lazy aggregate, I could have the subtree sums. If I want to progress it by some delta, I just take this matrix and just take whatever the delta is. So matrix, I take whatever the delta is for node I. So I raise it to that power, and then I end up getting this. So the problem here is we need this matrix to this power pretty quickly. We could use fast exponentiation, but coming back to that other observation, this number only gets up to 10 to the 5th. So just like we could pre-compute running sums, as we did in episode 0, we could pre-compute all values of m to the d for all d, less than or equal to n being from the problem. And I can do that by just a standard, I just break up the product, and this allows me to do some kind of running product. You'll see me compute that there. And so that's all you do is the push updates are still the same, but now what we'd like to do is we'd like to save these subtree aggregates going forward. So really, this is what I think is neat about this problem is it's almost like a matrix exponentiation problem, but in the update of a segment tree. And you'll see there's all kinds of bizarre stuff you can do in the updates or in the push changes in a segment tree, all kinds of weird modifications. So just seeing a bunch of different examples, seeing a bunch of different problems that mix these ideas will make you better at segment tree problems. So I'm definitely just going to go code this one so you can see how to implement it, and just go through some of these details and see what we can do. So I have some nice test cases I think I can run too on the system. If you go to the Algorithmic Engagements website, you can download data on your own and just test it yourself. I don't think there's a good judge for running this, unfortunately. Okay, so what I have here code-wise is I've brought in the segment tree that I coded during the Algorithms Live episode 4. And I've taken out some things. So I've taken out the update because I need to change that. But it's basically the same thing. So add's not going to change in terms of our segment tree. And sum query, I'm going to do a sum query. I'm just going to return that vector, that pair vector. Yeah, because I'm getting things back from the subtree. Although I'm starting to think that maybe I don't need it. Yeah, let's try coding this a little bit differently. So it's a little bit like a standard sum query. I'll just put in an update sum1 plus sum2. And if we completely cover the interval, I'm going to have to do something where I return what's in this interval cover. And then this piece right here is the case where I'm not really covered, so that's just return 0. Keeping things as longs. So I need to keep things under modulus. So use modo for modulus, and I'm not really sure why. I believe this is the modulus from the problem. Okay. So I'm going to write some of my standard stuff that I want to do, just like your standard problem code. So read in the input. So there are n items, that's the array size. K is number of queries. You need to make a segment tree. And then I loop through all the queries. And there are 2 types of queries. So but they're both on interval ranges. So we'll go like that. So the add query is exactly the same. I just pass in this is the root node, and this is increasing by 1. I could have changed this to not allow to increase by more than 1, but I just did by 1. Of course, I could make this problem any old value, and if the numbers got too big, I'd have to do, instead of pre-computing those matrices, fast matrix exponentiation. I'll have an extra log factor, but it'll still work. Still be fairly fast. And then I guess I need to print out the answer. So out.println. I'll do a sum query from 1 to these ranges. So that's pretty much the problem. So the next thing I need to do is I need to compute for every single one of these matrices all the powers of that Fibonacci matrix. So what I'm going to do here, I have no idea why I'm using longs everywhere. I'm going to just write a standard matrix multiply function. So given 2 matrices, figure out how to multiply these 2. I'm not going to write it generically, though. You could probably write one generically. I'm just going to do it for 2 by 2 matrices. This is going to be the slowest part of my code, probably. So my code's not as fast as it should always run. If you were doing a code forces problem, for example, and this matrix was this small, you might get TLE. So my advice here would be, in Java at least, my advice here would be, instead of making this a 2-dimensional matrix like this, make it 1-dimensional and have 0 and 1 be the first row, and then 2 and 3 be the next row. But just to illustrate the concept a little bit better, I'm going to code it this way. I think that this will just be easier to understand. So again, this is just the way matrix multiplication works. I start at what row I'm at, and I loop through the column on the first matrix. And then given some column in the second matrix, I loop through the row. And so I go like this in parallel, multiplying them together, each term together, and then add them as a running sum. You end up computing ij. And if you look at this code, you'll see some similarity, except for loop order, to Floyd's algorithm, Floyd-Warshall's, with slightly different operators here. So there is a relationship, and I'll probably talk about it when I cover Floyd's, between matrix multiplication and Floyd's. But that will be a different episode. Okay, so I also want to do some vector multiplication. Be useful in this problem. So this is, I wrote my multiply more generally. I wouldn't have to write code like this. But I'll write this anyway. This is just vector multiplication. I kind of want to put this under modulus too. All right. What I can do here is I can return that as well. Okay, so that's just your standard matrix multiply, vector multiply, and it's only going to work for 2 by 2. But you could easily generalize this if you really wanted to. Okay, so I need to compute some information for all the matrices. So what this is going to be is an array of 2 by 2 matrices. That's what mats is. And so I'll just write a function called genmats. And so it's like bad convention here, but maybe I'll do max edges this way, or max exponents. I guess that's what this is, max exponents. So I need to do that. And so this is just like any running sum you've ever written, except it's matrices. So Java, I can write this like this. So for 0, anything to the 0 power is 1. In matrix theory, anything to the 0 power is the identity matrix. That's what that is. So it's just diagonals all 1. Everything else is 0. And then I can also do this. And if you recall, this was the matrix that I wrote out on paper. Okay, and then I can just do my running product. That. This comes right from that equation. So it's m to the e is equal to m to the e minus 1 times m. So I've generated all the matrices I care about for this problem. Okay, let's go modify our segment tree. I think that's good use. Okay, so things we need to modify. So this is a segment tree in the init function. So usually in init, I don't do anything. You see like I write code like this. The problem is, I guess I should talk about what I'm storing in my thing. So the first thing I'm going to store is I'm going to store a new thing called sum. So inside every single node, I'm going to store a sum. It's really just 2 sums. It's the sum of the Fibonacci numbers that are the answer for this subtree right now, and the sum of that plus 1. Those are going to be the 2 sums I store in every single node. So I just need to save that for this subtree. So sum of I is going to be equal to new long, I guess I'll initialize it differently. Hold on. So I'll do sum equals new long 4 times n plus 1 by 2. So this is bad for memory consumption in Java, but good for the way I'm coding it. So I basically, all I'm doing is I'm saving the first 2 Fibonacci numbers in every single node. If you recall, the array is originally all zeros. And so this is handling that. And then, of course, I still return. Now, one thing that's changed here is I still need to do subtree aggregates. And so usually when I do this code for segment tree, I don't have anything to propagate down because I'm not making a modification. But if I do in init initialize something, I should also call update on that node on the way back. So that's important, small detail for solving these kind of problems. Okay, so speaking of update, let's talk about how we need to modify update. So originally, if you're doing like a min segment tree, this is kind of what update looks like. So it was something like this. Min value is min val of 2 times I plus delta 2 times I, and then min val of the right child. Something like that. That's typically how I'm dealing with min values in my segment tree. The problem is that's not going to fly for this problem. What I really need to do is what I was talking about, which is I need to progress whatever the sum of my subtree is. So sum of 2 times I is going to be 2 different values. I need to progress it by my delta. And so here's how I'm going to do that. I'll make a new array called left sum. And I'm just going to multiply it by that matrix that I wrote out. So delta 2 times I, that's the delta in the left subtree, times whatever the subtree sum was. And I do the same thing for the right sum. You'll notice the code is between these 2 versions. So this is subtree min up here. And this is this matrix multiplication stuff. It's really the same. I'm like applying delta to my sum. So if you're doing a segment tree, you have to do aggregate somehow, but you need to very quickly be able to apply your change, the aggregate of all your changes. So that's what I'm doing here. I'm just multiplying it by this sum, and I'm getting this left and right sum out, which is great because now I can update myself. Just replace it with ones, and we're good. Okay. So that was nice. And so this doesn't change. Now that I've coded update, anytime I call it, it's going to work correctly. So I'll just erase that code there. So my update works great. Sum works great. And this appears to be working. So now if I completely cover an interval, once again, I do have the same problem where I have to write kind of the same code for this. So I can just return, multiply the delta of I times the sum at I. So this is a complete covering. So if I do a complete cover, my delta might not have been applied yet. So I just apply it and then deal. And that's the easiest way to code that piece. And that's all I do to modify the segment tree. So it's a little bit of pre-comp here and then just a segment tree. So let's see if this ends up working. Ooh, didn't specify a type for the modulus. All right. Gonna make that 0. Need what's currently there. Let's see if, ooh, null pointer exception. So some delta that. All right, so it is going to be a null pointer. Huh. Gotta track down why this is null pointer though. That seems correct. Seems correct too. Update coming off of I. Left and right. I don't know why this is -1. It should be fine. Just in case. Know why that's, yeah, I still don't know why that's -1. Seems a bit weird to me. Some right, some left, some right, some would be the delta, right? But that seems fine. Oh, the matrix. That's why. Okay. I need to call my function I wrote. And I have a bug. Well, it should probably make sure multiply is working correctly. Okay, mat1 is wrong. It should be something in the comments. Oh, right. Whoops. Good call. It seems to be working now. So someone was asking, what is Polish Algorithmic Engagements? So it's just a contest. So if you look on the Algorithms Live blog, if you just search or click the link that's given, and then you go to Task Archive on the left of that page, what you'll see is Polish Olympiad in Informatics, but Algorithmic Engagements is another series of contests that they have. And I think it's just an open competition, it looks like, for, and it's run by Poland. And the problems are really cool. So that's really what that contest is. Yeah, and that's the name of the contest. So pretty cool. Let's see if this works testing wise. Oh, index out of bounds. Maybe that -1 I removed was not a good button to press. Let's put it back. Nope. Array index out of bounds exceptions. It's not a good night for me coding wise. And oh, whoops. I have to make my matrix big enough, not for the array, but for the number of queries. So you'll see the code as it's running right now isn't super fast. So it's running worst case about a second and a fourth. So if you want to try optimizing it, it's really just this being a two-dimensional matrix here is really killing me in Java. Small matrices like this aren't good. And maybe hard coding these multiplies is a lot better than these for loops. You could do some loop unraveling, which the compiler should be doing for me, but maybe it's not. Yeah, and that would be the biggest optimization, because the rest of this is pretty clean. It's really just that matrix multiply. Maybe doing this in a way that doesn't waste memory as bad as I'm wasting it here. I'm making a new array every single time here, but that's just for clean code more than optimizing it. So if I really played with this, I could get the runtime down quite a bit. But you do see that it is correct. Yes. All right, so thanks everyone for watching. I will say that this week I'm going to run a few episodes, more than just one, to make up from that other week. So Sunday I'll be running an episode. It looks like it'll be on topological sorts and Kosaraju's algorithm. And then I've got a few interesting weird episodes planned. And I want to run one on Wednesday this week as well. So just a few weird times to deal with some changes that are going to happen with where I'm going to be hosting the show. I'm no longer going to host it in my office. But I do want to run a few episodes before I make that move. So I'm going to run one on Wednesday, run one on Sunday. So lots of algorithms live back to back to back. So tonight you get one Sunday, you get one Wednesday. It should be pretty good. And then it should go back to more its usual time after that. Yeah, so we got one more question here. So it says, why is a 2x2 matrix bad? I thought 2D matrices were in row major order. They should be fine for cache performance. So it's less about cache performance here. It's more about how Java stores two-dimensional arrays. If you look at what it's actually doing here is it's making an object for every single array. Arrays are objects in Java, kind of. And so what we have here is an array of arrays. And that's way more memory than just a size 4 array. The other thing for cache performance is since they are objects, they may be in different parts of memory. So we are getting hit by cache performance, we're also getting hit by memory usage. And because look at this, I'm creating this matrix every single time I do a multiply. That's really killing me in some ways. So one thing I could do is I just want to show you how fast maybe the pre-comp is. The pre-comp might be killing me a bit too. So we can run that real quick. So I can, everything is going to fail, but that's a pretty slow pre-comp as well. I guess not the most expensive part, but so that's hitting me a little bit more than it should. And it's just this multiply in this loop right here. So one thing I can do is you can hard code the multiply if you have small matrices. It's usually a good idea. And I've been burned a few times on code forces doing something like that when I do virtual participation and things like that. But yeah. Anyway, yeah, C++ should be fine. Yeah, it should be fine in C++. I haven't seen people make much of an issue. And for static arrays, at least in C++, if you have multiple dimensional arrays, they under the hood are just flat arrays, just one big block of memory, and it's handling the indices implicitly on its own. So it doesn't seem like there should be a problem in C++. But thanks for watching, guys. I hope you enjoyed this episode, and I'll see you guys all on Sunday and on Wednesday this coming week.